Understanding the robots and where to use them. Chapter 2. Every robot is designed for a purpose. From the way it moves to the tools and sensors it carries, each platform is built with specific environments and challenges in mind. Choosing the right robot isn't just a technical decision. It directly impacts performance, safety, and mission success. In the following sections, we'll explore the most common types of robots and where each one excels. Let's start with LiDAR, short for light detection and ranging. It is a critical sensor in modern robotics, especially for missions that require high-precision environmental awareness. In search and rescue, LiDAR helps robots navigate rubble, collapsed structures, or debris-filled areas by creating real-time 3D maps. This allows responders to safely and quickly locate survivors while avoiding hidden hazards. During security patrols, LiDAR enables the robot to detect movement, map surroundings, and identify changes in terrain or layout, improving perimeter awareness and reducing blind spots. For infrastructure inspection, LiDAR systems can scan bridges, tunnels, pipelines, and buildings, detecting surface damage, deformations, or obstructions with centimeter-level accuracy. LiDAR is also essential for disaster zone mapping. Whether after a flood, earthquake, or explosion, robots equipped with LiDAR can assess damage, identify blocked routes, and build detailed 3D maps to support recovery planning. In short, LiDAR transforms a robot into a smart explorer, able to see, measure, and move through complex environments with speed, precision, and safety. SLAM stands for Simultaneous Localization and Mapping. It's a core technology that allows a robot to build a map of its surroundings while keeping track of its own position within that map at the same time. SLAM systems use a combination of LiDAR, cameras, inertial measurement units, IMUs, and wheel encoders to understand movement in space. This allows the robot to navigate unfamiliar or dynamic environments without relying on GPS. In real-world missions, like tunnel inspection, search and rescue, or underground exploration, GPS may be unavailable or unreliable. That's where SLAM comes in. It enables the robot to create accurate 2D or 3D maps on the fly, while planning safe paths, avoiding obstacles, and adapting to changes in the environment. SLAM is what gives modern robots the ability to explore, learn, and move through the unknown, autonomously and intelligently. Let's take a closer look at what an IMU, inertial measurement unit, actually does. First, it helps determine the robot's orientation, specifically tilt, pitch, and roll. This tells the robot how it's positioned in space, which is critical for staying balanced and aligned. Next, it measures motion and rotation. By detecting changes in speed and direction, the IMU allows the robot to understand how it's moving, whether it's turning, accelerating, or even falling. This plays a key role in balance and navigation, especially for dynamic platforms like drones, quadrupeds, and mobile robots. Without an IMU, these robots wouldn't know how to correct themselves or respond to uneven terrain. For example, an IMU helps a drone stay level in the air, even when the wind pushes it off balance. Or, in a quadruped robot, the IMU allows it to adjust its legs in real time as it walks over rocks or slopes, preventing a fall and maintaining stability. In short, the IMU acts like the robot's inner sense of motion and orientation. Just like our inner ear helps us keep our balance, robots extend their sensing capabilities far beyond vision and sound. Today's platforms can be equipped with tools like thermal cameras, gas detectors, LiDAR scanners, and vibration sensors, enabling them to detect temperature changes, hazardous gases, structural shifts, or terrain geometry. Combined, these sensors create a rich, real-time picture of the environment, supporting tasks like fire detection, gas leak identification, mapping confined spaces, or navigating in low visibility conditions. In advanced systems, facial recognition may also be used to identify individuals, detecting unauthorized access, confirming identities, or issuing alerts when specific profiles are detected in restricted areas. Robots don't just complement existing surveillance, they extend it. Instead of relying solely on static cameras, organizations can deploy mobile robots to patrol blind zones, follow dynamic threats, or verify alerts visually and thermally. Finally, GPS tracking allows both the robot and targets, such as personnel or equipment, to be located and monitored. Robots can trace routes, track movements, and geotag areas for follow-up inspections or incident response. Together, these capabilities transform robots into intelligent agents, enhancing visibility, reducing risk, and improving mission outcomes in sectors ranging from industrial maintenance to critical infrastructure security. Now, let's explore the different types of robots, beginning with one of the most common and efficient platforms, wheeled robots. Among the most common and versatile robotic platforms, these systems typically use 2, 4, or more wheels powered by electric motors, delivering efficient, fast, and energy-conscious mobility. Their mechanical simplicity allows for high speeds, long runtimes, and relatively low maintenance, making them ideal for routine tasks in structured environments. Wheeled robots perform best on flat, even surfaces such as factory floors, warehouses, hospitals, and office buildings. As such, they are commonly deployed for material handling, inventory tracking, delivery tasks, and automated security patrols. Many use differential drive systems, where 2 wheels on opposite sides operate independently to allow tight turning and precise movement. Some advanced platforms use omnidirectional or mecanum wheels, enabling lateral or diagonal motion, especially useful in narrow or crowded spaces. Next, let's look at tracked robots. These robots excel in harsh environments, tunnels, disaster rubble, construction sites, and debris-strewn terrain. They can climb steep slopes, traverse obstacles, and handle conditions where wheels struggle, making them ideal for search and rescue, underground inspection, and off-road reconnaissance. Sensors commonly integrated into tracked platforms include LiDAR, thermal cameras, and inertial measurement units, IMUs, enabling autonomous navigation and environmental mapping in GPS-denied or visually challenging conditions. Now, let's dive into quadruped robots, 4-legged robots that mimic the locomotion of animals, such as dogs or horses. These robots are designed to navigate complex, unpredictable environments where wheeled or tracked robots might struggle. Ideal for urban patrol, infrastructure inspection, and search and rescue, they can navigate debris, enter collapsed buildings, assess hazards, deliver supplies, or locate survivors, tasks too dangerous for humans or traditional robots. With LiDAR, depth cameras, and IMUs, quadrupeds create detailed 3D maps for autonomous navigation and obstacle avoidance, even without GPS. Now let's explore single-rotor and tethered UAVs, unmanned aerial vehicles that provide a unique advantage: the ability to observe from above. Single-rotor drones are battery-powered and fly freely, typically offering 20 to 60 minutes of flight time depending on payload and conditions. These are often used for infrastructure inspection, emergency response, agriculture monitoring, and situational awareness in areas that are difficult to reach on foot. Tethered UAVs connect to a ground station via a lightweight cable that delivers continuous power and high-bandwidth data. This lets them remain airborne indefinitely and stream video or sensor data in real time with minimal latency, ideal for surveillance and monitoring. They're especially effective for long-duration missions like event security, border patrol, and disaster response, where constant overhead visibility is critical. Both vehicle types can carry a range of payloads, including high-resolution cameras, thermal sensors, LiDAR, and GPS modules, providing accurate data collection and navigation capabilities. Humanoid robots mimic the human form with arms, legs, and a torso, allowing them to use existing infrastructure and tools without major modifications. Highly adaptable, they perform tasks in manufacturing, logistics, healthcare, customer service, and emergency response. Their dexterous hands, multi-jointed limbs, and advanced sensors, LiDAR, stereo vision, tactile feedback, enable delicate handling, machinery operation, navigation of stairs, and safe human interaction. While slower and more complex than wheeled or tracked robots, their versatility and human-centric design make them ideal for mixed human-robot environments and next-generation applications. Beyond mobility, robots excel at intelligence gathering. Wheeled, tracked, quadruped, or aerial platforms can carry sensors to see, hear, and sense their surroundings in real time, extending operations into dangerous or inaccessible areas. For security, inspection, or emergency response, these mobile data collectors boost situational awareness, decision-making, and mission safety. High-resolution cameras enable live streaming, motion detection, and patrol recording, covering blind spots and tracking intruders beyond the reach of fixed CCTV. Audio sensors, like directional mix, can detect unusual sounds such as breaking glass, mechanical faults, or unauthorized voices. In reconnaissance, compact and quiet robots can discreetly scout ahead, stream live intel, and navigate hazardous zones without risking personnel. This table compares two levels of robot SLAM capabilities: Basic SLAM and Industry-Grade SLAM. Basic SLAM handles core functions like localization, obstacle detection, and standard navigation, ideal for simpler, flat indoor environments. However, when your mission involves complex, large-scale, or multi-floor environments, Industry SLAM is a must. It supports advanced mapping scenarios, such as utility tunnels or multi-map switching, and uses RTK fusion for highly precise positioning. For navigation, Industry SLAM goes beyond obstacle avoidance. It enables stair climbing, robot posture control, speed adjustments, and full floor-to-floor autonomy. It even allows automatic locomotion switching depending on terrain. On the general side, both support OTA updates and mobile app control, but only Industry SLAM gives you integration with modern protocols like WebSocket and web-based interfaces, critical for remote access or enterprise integration. Ultimately, if your application demands robust, intelligent, and adaptable performance, Industry SLAM is the way to go. When choosing a robot for a specific mission, it's important to match the robot's strengths with the job requirements. Let's look at some common real-world applications and the types of robots best suited for each. Drones and robotics are transforming multiple industries through automation and smarter data collection. In energy and utilities, drones and tracked robots can be used for infrastructure inspections and asset monitoring. In agriculture, drones support crop monitoring, precision spraying, and yield prediction. This sector also shows high growth, fueled by smart farming technologies. Construction and real estate benefit from both drones and terrain robots in site surveying, progress tracking, and media documentation. In mining, drones are commonly used for site mapping, environmental monitoring, and stockpile analysis, especially in remote or hazardous locations. Public safety and emergency services, tracked, wheeled, and drones can assist with search and rescue, disaster response, and surveillance, boosted by adoption from local governments. Finally, telecommunications uses drones for tower inspections and 5G infrastructure planning. Some of these environments can be dangerous or inaccessible for humans. For these missions, tracked robots and quadruped robots are ideal. Tracked robots offer excellent stability and traction on rough or unstable surfaces. Quadrupeds can navigate uneven terrain, stairs, and obstacles, making them versatile in complex environments. Both types can be equipped with advanced sensors to detect chemicals, radiation, or structural damage, while keeping operators safe at a distance. Drones are perfect for inspection and surveillance. In Chapter 4, we'll explore in depth how to choose the right robot for your mission.